Electron orbitals. Orbits and orbitals sound similar, but are very different. The impossibility of drawing orbits for electrons. To plot a path for something, you need to know exactly where the object is and are able to work out exactly where it's going later. You can't do this for electrons. The Heisenberg uncertainty principle says that it's impossible to find with absolute precision at the same time both the position and the momentum of an electron, which means you can't know with certainty both where an electron is and where it's going next. This makes it impossible to plot an orbit for an electron around a nucleus. Hydrogen's electron, the first orbital. If you have a single hydrogen atom and at a particular instant plotted a position of one electron, soon afterward you'll do the same thing and find that it's in a new position. You have no idea how it got from the first place to the second. You keep on doing this over and over again and gradually build up a sort of a map of the places the electron is likely to be found. In hydrogen's case, the electron can be found anywhere within a spherical space surrounding the nucleus. This diagram shows a cross-section through the spherical space. 95% of the time, the electron will be found within a fairly easy to find region of space quite close to the nucleus. Such a region of space is called an orbital. Each orbital has a name. The orbital that occupies a hydrogen electron is called the first orbital. The 1 represents the fact that the orbital is in its energy level closest to the nucleus. The S tells you the shape of the orbital. S orbital is spherical symmetrical around the nucleus. The orbital to the left is a 1s orbital. This is similar to a 1s orbital, except for the region where the greatest chances of finding an electron is further to the nucleus. This orbital is the second energy level. 3s and 4s, etc. orbitals get progressively further from the nucleus. P orbitals. Not all electrons inhabit s orbitals. At first, the energy level of only orbital available to the electron is a 1s orbital, but at the second level, as well as the 1s orbital, there are an orbital called the 2p orbitals. A 2p orbital, rather than two identical is like two identical balloons tied together at the nucleus. Once again, the orbital shows that this is a 95% chance of where you can find a particular electron. Unlike the s orbital, a p orbital points in a particular direction. The one drawn points down the page. The p orbitals at the second energy level are called 2px, 2py, and 2pz. The similar orbitals are subsequent levels 3px, 3py, 3pz, and 4px, 4py, 4pz, and so on. All levels except for the first level have p orbitals. At higher levels, the lobes get more elongated, with most likely place to find the electrons more distant from the nucleus. D and F orbitals. In addition to S and P orbitals, there are two other sets of orbitals which have become available for electrons to inhabit at higher energy levels. At the third level, there is a set of 5d orbitals, as well as 3s and 3p orbitals. At the third level, there are a total of 9 orbitals altogether. At the fourth level, as well as 4s, 4p, 4d orbitals, there's also an additional 7 f orbitals, 16 orbitals in all. S, p, and d and f orbitals are then available at all higher energy levels as well, fitting electrons into orbitals. You can think of an atom as a house, the nucleus living on the ground floor, and the various rooms, or orbitals, on the higher floors occupied by the electrons. On the first floor, there is only one room, the 1s orbital. On the second floor, there are 4 rooms, the 2s, the 2px, the 2py, the 2pz orbitals. On the third floor, there are 9 rooms, 1 3s orbital, 3 p orbitals, and 5 3d orbitals, and so on. But the rooms aren't very big. Each can only fit 2 electrons. A convenient way of showing the orbitals living in is to draw an electron in boxes. Electron and boxes. Orbitals can be represented by boxes within the electrons to show them as arrows. Often an up arrow and down arrow are used to show the electrons in some different ways. A 1s orbital holding 2 electrons could be drawn and even more quickly as a 1s squared. This is read as 1s2, not 1s squared. You must not confuse the two numbers in this notation. The order of filling orbitals. The Adolphi principle. Adolphi is a German word meaning build up or construction. We imagine as you go from one atom to the next periodic table, you can work out the electron structure from the next atom by fitting it an extra electron to the next available orbital. Electrons fill low energy orbitals before they go to higher ones. When there is a choice between orbitals of equal energy, they fill the orbitals slightly as far as possible. The filling of orbitals singly is where the possible is known as Hund's rule. It only applies to the orbitals that have the exact same energy to keep them that helps to minimize the repulsions between electrons, so it makes the atom more stable.